So centripetal force. Centripetal force is the force that's directed towards the center of the circle for an object that's traveling in uniform circular motion. Okay. Centripetal force is the force. That's like Yoda when I said the force. Okay. The force directed towards the center of a circle that keeps an object in UCM. Remember what UCM stands for? Anybody remember?
Uniform circular motion.
Good, uniform circular motion. Oh, that's a terrible circle. University of Comstock, Michigan. Right? Okay. It's a little better circle, not great. There's my circle, right? Let's say I have a rubber stopper or a planet or a satellite or something that's going around in the circle. Right? Which way does the centripetal force point? Towards the center. The centripetal force points towards the center. Right? At any location. So from up here. Over here. Okay. So at any location, the centripetal force points towards the center. Now think for a moment which way the acceleration points. Don't shout it out. This is branch. I can. Yep. Richard, what'd you do?
I think you forgot points after
Did I? Okay. The force directed towards the center of the circle that keeps an object in UCM. Okay. Richard, you gotta go to the office. I think I told him. Alright. So, the force directed towards the center of the circle that keeps an object in UCM. So I asked, which way is the acceleration? The same direction. Why the same direction, Maria? What? Why the same? Why towards the center? So Maria says the acceleration is this way as well. Are you using my definition of uniform circular motion from earlier? You think so? Anyone help Maria besides the definition of uniform circular motion? Why are the force and acceleration in the same direction? You just throw out all those geometry terms, don't you? Another parallel right there, Kevin. They point in the same direction, not perpendicular. They're perpendicular to another quantity, though. What are they perpendicular to, Kevin? The velocity. Good. Kevin, sometimes your geometry vocabulary helps us out. Sometimes it takes us to a place we don't want to go. That time it helped out. All right, so it's a guessing game. So Maria, you are right. Acceleration and force are in the same direction. But why? There's something this one guy thought of at one time. It's really kind of important, dude. Apples hit him in the head every now and again.
Oh, the gravity law guy.
The gravity law guy. What's his name? Newton. Okay, how many laws did he have? Three. Which one applies to force and acceleration? Second law. What does second law tell us? F net words. MA, right? Newton's second law, right? Okay. A centripetal force. Okay. A centripetal force. The centripetal force represents the net force acting on the object. Okay. So the centripetal force is just like a net force. Okay. Maybe we'll put after it net force towards center of circle. Okay. That's kind of a good definition of centripetal force. It's a net force towards the center of a circle. I know I have this other definition for you there. But the centripetal force essentially is the net force of the object being pulled towards the center of the circle on which the object is rotating around. So this F net right here, this is really what? This F net right here is really centripetal force. In this case, F net is FC. And FC equals MA. If I'm traveling in a circle, this A isn't just an acceleration, it's a... Nope. What, a little louder then?
Centripetal acceleration.
That A is a centripetal acceleration. Does anybody remember the equation for centripetal acceleration? A little c equals
V divided
V squared divided by radius, right? So FC equals M V squared over R. And that right there is our centripetal force equation. Okay. Now, earlier when we were talking about the rubber stopper and the wooden handle, right? And the washers. Right? When we were talking about this demo. I'm afraid to hit myself in the face. I'm going to swing it vertically this time. We're talking about this demo, right? Right. We came up with a relationship between velocity and radius that showed V and R, V over R is proportional to a constant, right? Right? Or that R is proportional to V. Does this equation right here, does that show that same relationship?
Yeah.
Does this show that a constant is proportional to V squared over R?
Yes.
So does it agree with your findings using the rubber stopper and the wooden handle?
Yes.
That as velocity increases, what happens to the radius? It increases. Okay. Now, I said that works as long as something is constant, right? What did I say was constant? Not speed, because remember we increase the velocity, increase the radius. Okay. The mass of the rubber stopper, we don't change the rubber stopper's mass, do we? Same rubber stopper the whole time. Right? What else has to be constant? If V is changing, V is getting bigger, and so is R, right? Remember our relationship said they had to be proportional to something that's constant, right? So that means what else is constant here? Our centripetal force. Good. The centripetal force is constant. Why was the centripetal force constant with this situation? Why is it? Why is centripetal force constant in this situation? What's not changing? The washers. These washers are not changing their mass. Right? These washers are not changing their mass. Their mass is staying the same, right? And since their mass is staying the same, what happens to tension? It stays the same. Okay? And if we look at this rubber stopper going around the circle, okay, the thing that's keeping it in the circle is the tension of the string. And the tension of the string is supplied by the mass of the washers and the force of gravity acting on them. So as long as we didn't add more washers to the situation, the mass stayed the same, which led to the tension staying the same, which led to the centripetal force staying the same, right? They're all the same, weren't they? So that means that this force centripetal right here is a number, right? The mass of the washer is a number, right? So if I increase my velocity, what has to happen to the radius to keep this number the same? Radius has to increase. Now, is it a 1-to-1 increasing? Juan, you're shaking your head? No. Why isn't that 1-to-1, Juan? Because the velocity is squared. Okay. If the velocity goes from 1 to 2, the radius has to go from 1 to 4. Right? If the velocity goes from 2 to 3, right? The radius has to go from 4 to 9. Okay, it's not a 1-to-1 increase. Right? And that's why there's a little optical illusion that makes it look like the washers or the rubber stopper is actually traveling faster at smaller radiuses. Because our eyes can't keep up with it because it's going around the circle so quickly. But that velocity stays the same. I think you guys know what I'm talking about. When the rubber stopper's like this, it looks like it's all kind of all going together, right? If I let more string out, it's still going the same velocity, all right? But I don't see that constant black ring around the center, right? That's because my eyes can keep up a little better with the rubber stopper out here. My eyes can separate bands of where the rubber stopper could be and where I know it's not, right? When I go in here, my eyes aren't that good to separate the rubber stopper from the things around it, right? So it's more of your eyes playing tricks on you than it is the actual velocity of the rubber stopper. Right? All right, are there any questions? Any questions about the centripetal force equation? Yes, Michael.
Wait, when do you use these equations on a problem?
When do I use these equations in the problem? So, do you do the homework? Let's do today.
Yeah.
All right. Problem 13.
Yeah.
Where they talk about a runner going around in a circle, and they said, what's the force of friction acting on the runner? Right? Well, if you know the velocity, you know the radius, you know the runner's mass, right? If they're going around in a circular path, just like here, okay, if I'm running around in a circle, the thing that's keeping the runner in that circular path is the friction between their feet and the ground, right? So this centripetal force, which is like a net force, can be any force. It can be friction, it can be tension, it can be gravity, it can be electromagnetic attraction, okay? It can be anything because it's like a net force, okay? So if it's a runner going around in a circle, this centripetal force is friction. Good. Okay? So we can figure out the friction force acting on the runner by doing mv squared over r. Okay? Or if I know the mass of the rubber stopper, right? If I know the mass of my rubber stopper in the wooden handle example, and I know the radius of the circle it's going in, and I know its velocity, we can then figure out the tension in the string. Okay? If I know the mass of a satellite that I sent to Jupiter, okay, maybe not Jupiter, that's too far. If I know the mass of a satellite that I sent around Mars, right, I know its velocity, I know its orbital radius around Mars, okay, so I know the mass of the satellite, its velocity, its orbital radius, then I can figure out the force of gravity at that point from Mars, which we then can actually work back, and I'll show you later on in this unit, we can actually work backwards to actually figure out the mass of Mars. Okay. Same thing with us. We know the mass of the Earth. We know our velocity and our path around the sun. We know the radius of our path around the sun. So then we can figure out the force of gravity the sun exerts on us, which we then can work backwards and figure out the mass of the sun. Right? So there's plenty of things we can use this equation to. All right? All right. Are there any questions? Any other questions about the centripetal force equation? Yeah.
So in this case, you can find the centripetal force by using gravity force, like M times G, using the washer.
We know the mass of each washer, and we're looking at the situation where the rubber stopper is going around and the radius is increasing, right? If we know the mass of each washer, we can figure out this tension. And we said since we didn't change the washers, we know this tension is the same at all those locations, right? So since the tension is the same at all those locations, we could actually figure out the velocity or the radius depending on what we need. Are there any questions? All right. So let's look at that spiraling out drawing that I attempted to make. All right. So once again, this is the rubber stopper at a couple of locations. As the what's increasing for the rubber stopper? What do we say was increasing? The velocity. And we said the tension was the same at all the locations because we didn't change the mass of the washers, right? Right? So in this situation, the velocity is increasing. Right? Let's just put some arbitrary numbers with it, just to, I guess, explain a little more why the radius increases. All right? So, what do you guys want to call the force of gravity? Just give me a number.
11.
11. Perfect. We'll call the force of gravity 11 newtons. Okay. That means this tension force is what? 11 newtons. So that means that all these locations, force tension equals 11. I'm going to pick 3 locations. We'll go that one. We'll go with this one. We'll go with this one.
Did you make a J?
Yeah, kind of looks like J, didn't it? Okay. So say at all three of those locations, we know the force tension is 11 newtons thanks to Sergio. Okay. Any questions? Any questions? Anyone want to pick a mass rubber stopper? It can be an easy number. A pi? We're not going to go pi. It's a little difficult. Easiest mass rubber stopper. What do you guys think?
3.
I was thinking easier. Let's go 1 kilogram. Okay. Sergio, do you only use 3 or can I use 1? I can use 1? Okay. So, let's say this radius right here, let's say the velocity here. Let's say the velocity here is 2 meters per second. Okay? Just arbitrarily picking that. Alright, it's not data actually collected. I'm just showing you why the radius has to increase. Okay? Let's say the velocity here is 3 meters per second. Okay? Let's say the velocity down here in our last location is, anybody find the trend? 2, 3, 4 meters per second. You guys are problem solvers. Okay. So at our 3 locations, maybe we should name them to make it a little easier. We'll call this A, B, and C. At A, we know that M is 1 kilogram, the mass rubber stopper. We know the force tension, which is the centripetal force, right, is equal to 11, right? And we know the velocity is 2 meters per second. We want to find the radius, right? Well, before we get into doing that, I'm going to try to simplify our work here. I'm going to try to simplify our calculations. We know that Fc equals mv squared over r, right? What's Fc going to be in every one of these situations? 11, because we're not changing the washers, right? Okay, so Fc is going to be 11. What's the mass over stopper going to be in every situation? 1. So every one of our problems will look like this. 11 equals 1 v squared over r.
Can't you fill in for B too?
We can at each location, right?
Yeah.
But every problem will end up looking like this. 11 equals 1 v squared over r, right? Right? So if I solve this for r, if I multiply both sides by r, we get 11r equals v squared, right? Now I'm going to divide by 11. We end up with r equals v squared over Sergio's 11. Right? Does that make sense? So now I have an equation for my radius in terms of my velocity. And does this still show that direct relationship we talked about? Does this still show the direct relationship? Okay. And why is this 11 in every situation? Why would we say that? Did the centripetal force change?
No.
No. That's why we have this constant 11. Did the mass of the rubber stopper change?
No.
No. That's why we have this constant 11. Okay, does that make sense? Does that make sense, guys? Yeah. Okay. So now as we increase the velocity of the rubber stopper at those 3 points, as I increase velocity, what has to happen to radius?
It also increases.
It also increases. Good. It has to increase, right? Because of this relationship. So I'll prove it to you. Velocity is 2 here, right? So our radius will equal 2 squared over 11, which is 4 over 11. Not go with fractions that add 11 in them. 4 over 11 is like 0.38, I'm guessing. 0.36? Oh, man, close. 0.36. That makes sense because 10 minutes. It makes sense. All right. So 0.36 meters, right? Now, for part B, point B, what's the only thing that's changed?
Velocity.
Velocity, right? So, if the only thing that's changed, we still have the same mass and force. Velocity's changed to, not 4 yet, velocity's changed to 3, right? We still have this relationship, r equals v squared over 11, right? We can find our new radius. R equals 3 squared over 11. 9 divided by 11, 0.81. So what happened to our radius?
Got bigger.
It got bigger. Right? Did force change? No. Was there any outward force in this situation? Did I have to write an equation for the outward force acting on the rubber stopper? No. The only reason why the radius of the circle got bigger was because the velocity was bigger. Okay. Look at part C. Or sorry, location C. V equals 4 meters per second. Right? Radius equals V squared over 11 still. So that equals 4 squared over 11. 16 divided by 11, what's that? 1.45. Thank you. So the radius increased again because velocity increased. Okay. I would say the easiest way to kind of wrap your head around what's going on, because I think some of us might still be holding on to the idea that the rubber stopper moves outward because there's a centrifugal, I put an F in there this time, there's a centrifugal force pulling it outward. Right? Who still holds on to that idea? If you do, it's okay. You know what I'm talking about? Okay. When I did the water bucket example, right? Were you here for the water bucket example?
Yeah, when he's going around.
Yeah. Throwing the water on the bucket, right? Some student false conceptions is that the water stays in the bucket because there's an outward force pulling it out. Okay. That same misconception or inaccurate conception can be stretched to this example and saying the reason why the rubber stopper gets a bigger radius is because there's a force pulling it outward. Right? So what I'm trying to show you here is that there's no such force pulling this rubber stopper outward. The only reason why the rubber stopper moves outward is because what changes? The velocity. If the velocity gets smaller, what will happen to the rubber stopper? The radius will get smaller, right? It'll move closer to the handle. If velocity gets bigger, what happens to the rubber stopper? It moves away. Okay? So there it is mathematically. I've shown you with numbers that as velocity goes up, radius increases, right? So now here's the question, why does it work in every situation? Is everybody okay if I erase this? You guys good if I erase this?
Yeah.
Every one of these parts came back to this equation right here. FC equals mv squared over r. Right? In the rubber stopper example, in the water bucket example, right? Force centripetal equals mass times velocity squared over radius. In every one of those examples, whether it's me swinging the rubber bucket around with at a constant speed, or it's a rubber stopper going around in a circle, in every one of those examples, there's a centripetal force pulling the object towards the center, right? Right? If the velocity of the object is too big, what happens? It flies out, right? Okay. Let's take a look at this again. We said the force tension is 11 newtons, right? Let's say I'm at 11 newtons at this first radius. We said this first radius was like 0.36, right? And this one was 0.81, and this was 1.45, right? Let's say the first radius is at 0.36. Okay? We said our force tension was 11, didn't we? So that means 11 equals 1 over 0.36, right? Now let's say instead of my velocity being 2 at part A, my velocity is 3. $11 equals 1 times 9 over 0.36. What's 9 divided by 0.36?
I'm gonna guess and say it's 11.
No, it's not 11. What is it? 25. Is that equality true? No. 25 is too big, isn't it? Right? So this mv squared quantity is bigger than the force tension. So what has to happen to my radius? It has to increase. So instead of being 0.36, my radius has to be bigger. What does it have to be? We figured it out. 0.81. So if I do this whole thing again, but instead of 0.36, I have 0.81 on bottom. 1 divided by 9 or 1 times 9 divided by 0.81.
11.
We get 11, don't we? Right? So I'm trying to show you is that for every force, velocity, for every force and velocity, there's a certain radius they have to be at to make this equation equal. And that's why the rubber stopper moves out. The velocity is too big to make this equation equal. The radius has to compensate for that. Okay, Rich, you have a question?
Can't you just like hold the string and like spin it really fast?
I could, but that means I'm applying a bigger force, right? If I hold the string, and hopefully I don't make the rubber stopper break loose. If I hold the string, I'm pulling on it, aren't I? Right? So am I applying a bigger force than the washers? Yeah. Right? So then I've increased force, so now my velocity can go up if I keep the same radius. Does that make sense? Okay. The same is true with cars going around turns, especially right now. If I try to take a turn at the same speed I did in the summer, right? What's going to happen to my car?
You're gonna hit a snowbank.
I'm going to hit a snowbank because my force, the force of friction, has it gone up or down? It's gone down. So that means my velocity has to go down because the turn still has the same radius. Okay. Yeah, unless we're drifting around.
Yeah.
All right. Any other questions? All right. Nice job, guys.